we had studied coupled oscillators. In today's class, let me show you a simulation of coupled oscillators. So, in the simulation we have 3 springs, and these 3 springs are connected to 2 masses just like we had studied. So, we could set the value of the spring constants and the masses. So, let us go straight ahead and set the value of the spring constant. So, let us set K1, which is the first spring, let us set the value to 100. Let us set the mass, the first mass to 1. Let us set the second mass to 20, the second spring to 20, the second mass again 1, and the third spring to 100. So, this spring has a spring constant 100, this spring also has a spring constant 100 just like we had studied. This mass is 1, this mass is 1. So, these 2 springs have same spring constant. The spring in the middle has a lower spring constant of 20. So, it is not exactly in the very weak coupling regime, but it is quite weakly coupled still. Now, let us start off by putting a displacement to the particles such that we only excite the slow normal mode, that is we only excite the motion of the center of mass, that is the first thing we shall do. So, we shall put a displacement which will excite only the center of mass. So, to do that we have to displace both the particles by exactly the same amount. So, let me displace this by 20, also displace and give no velocity to this particle, this again by 20 and no velocity to this particle. So, both the particles have been provided the same amount of displacement. Now, let us see the oscillations. So, you can see that this kind of displacement disturbance where I give both the particles the same displacement excites only the first normal mode. So, it only excites q naught, which is x1 plus x0 plus x1 by 2, the motion of the center of mass. Now, let us look at a displacement, a disturbance which will excite only the second mode, which is the relative motion. So, let me put a magnitude of 50 and minus 50. So, they are both being given exactly opposite, and you see that the center of mass does not move, it causes only both the particles to do relative oscillation. And the pictures over here show you the motion of the blue mass and the yellow mass respectively. So, this shows you x as a function of time, and they are moving exactly out of phase. If you had looked at it at the same thing for the q0 mode, the center of mass mode, they would have been moving exactly with the same phase. So, what we have done is we have looked at 2 different kinds of disturbances, one which excites only the center of mass mode, the slow mode, another which excites only the fast mode. Now, let us consider a situation where I keep one of the particles fixed and displace only the other particle. This should excite a combination of both these modes. So, let us, which we have studied. So, let us now consider this particular situation. So, I am going to apply a displacement only to the first particle and leave the second particle exactly where it is. So, notice what is happening. We had initially given a disturbance only to the blue particle, now the disturbance has shifted from the blue particle to the yellow particle. Again it is going to shift back and then forth, etc. So, this is what we had studied. So, now it has gone to the yellow particle, now both of them are in oscillation, and slowly the yellow particle will come to rest and the oscillation will be fully back in the blue particle. So, you can see the same thing over here. The displacement is initially applied to the blue particle, the yellow particle starts from rest, and then the blue particle does this fast, both of them do this fast oscillation, and it has a modulation which is modulated. The modulation causes the amplitude of the blue oscillations to die down slowly and the amplitude of the yellow oscillations to pick up, and then the amplitude of the yellow oscillation goes down, the amplitude of the blue oscillation picks up. So, the oscillations go back and forth. Now, we could see what happens if I vary, if I increase the coupling between the two oscillators. So, if I increase the coupling, I would have to increase the spring constant of the spring in the middle. So, I am increasing it to 50, and if I increase the coupling between, I would expect the modulation to occur faster. So, I would expect the oscillations to go from here to here and come back much faster. So, let us see if it happens. This is what our analysis leads us to believe. So, now the blue particle has nearly come to rest, the yellow particle, now again the blue one has picked up, the yellow one has slowed down, and this will go back and forth between the blue and the yellow particle. Now, both of them, yellow one is picking up again, the blue is going to come to rest, now the blue is again picking up. So, the oscillations will go back and forth. We could also reduce the coupling, oh sorry, no, we could also reduce the coupling of the spring in the middle and see what happens. So, we have I have reduced the coupling of the spring in the middle. So, the disturbances are going to go from the blue to yellow particle very slowly, the coupling is very weak. So, the modulation is a much slower modulation, and you can see it here also. The modulation is much slower. The blue particle oscillation have just died down and the yellow ones have picked up. Now, again the blue is picking up and the yellow one is dying down, and it is going to keep on go back and forth between the blue and the yellow oscillations. So, let us stop our simulation here and go forward to discussing an entirely new topic, the sinusoidal plane waves, and you shall see later on that these waves arise in a situation when you have many oscillators coupled together. So, let us start upon our discussion of sinusoidal plane waves. We have been studying the motion of oscillators. We studied a single oscillator and then we also studied two oscillators which were coupled. In both situations, we studied the motion of a single variable or two variables as a function of time. So, time was the parameter and we studied the oscillations as a function of time. Let us now go on to a situation where we have oscillations which are a function of both space and time. Such disturbances, such oscillations are what are referred to as waves. We shall start our discussion of waves with the simplest possible situation, which is called the sinusoidal plane wave. So, the equation for a sinusoidal plane wave is shown over here, and we have A represents the oscillations, is the quantity that oscillates, and A is a function of x and t. So, we have oscillations that are a function of both position and time, and this is equal to some amplitude A into cosine omega t minus kx plus psi. So, this is what we refer to as a sinusoidal plane wave. In complex notation, we can represent this as A tilde, which is a function of x and t. So, you should remember that only the real part of A tilde is A, the imaginary part is to be rejected when we ask what is the real thing A. And we can represent this equation through this complex equation over here, where a tilde, which is a function of x and t, is equal to a tilde e to the power I omega t minus k x. Remember that the phase psi has been absorbed inside this complex amplitude. The complex amplitude a tilde is actually a into e to the power I psi. So, now let us discuss this particular sinusoidal plane wave in somewhat more detail. So, the first thing is, let us ask the question, what do we mean by this a x, which is a function of x and t? What is the physical quantity that this a, which is a function of space and time, which is the quantity that oscillates as a function of space and time, what does it represent? Now, the physical significance of a depends on the situation which we are analyzing. So, the physical significance that you attach to this variable a depends on the physical situation that we are analyzing. For example, if we are analyzing sound waves, we know that sound is actually a disturbance, it is a wave which propagates in air. So, when you have some source of sound, for example, a loudspeaker or the diaphragm inside our throat, inside our throat, these are sources of sound. Or when you ring a bell, for example, in the loudspeaker there is a diaphragm which moves, and when the diaphragm moves forward it compresses the air, when the diaphragm moves backward it rarefies the air. Now, when you compress air, so if you compress some air, you basically increase the density of the air. If you adiabatically increase the density of air, the pressure of the air goes up, and this causes it to, when the pressure of the air goes above the surrounding pressure, this will expand and it will push the air which is outside. So, this part of the air will push the air outside and it will cause the air the neighboring bits of air to get compressed, which in turn will again expand and then push. So, you have a disturbance which propagates. The disturbance is essentially a fluctuation in the density of the air, and it is this fluctuation in the density of air which is the wave, it is this quantity which oscillates. So, when you are dealing, for example, with sound waves in air, then the density of the air at any point at any given time t can be written as the sum of a constant density which would be there if there were no disturbance, if there were no sound waves, and there would be a disturbance, there would be a change in the density due to the sound wave, and this change in the density is a function of x and t. The density which is there when there is no disturbance is a constant. Now, when you are discussing sound waves in air, a of x and t represents the fluctuation in the density. So, when you are discussing sound waves in air, the variable a represents the variable is to be interpreted as representing the fluctuations in the density delta rho. If rho is the density of the air, then a represents delta rho, the fluctuations in the density. Now, we know that in air, when you have a sound wave in air, and if the disturbance is propagating in this direction, then the density change, the change in the density is also in the same direction. The density gets contracted and rarefied in the same direction in which the wave is propagating. Such a wave is called a longitudinal wave. So, sound wave is a longitudinal wave, and the quantity that actually varies with x and t is the fluctuation in the density, is the change in the density, and a of t represents this change in the density. We could also discuss another situation. Consider a string, a long string, consider a long string which is stretched and taut, it is stretched so that it is taut. In this string, if you introduce a disturbance which is perpendicular to the string, then such a disturbance will propagate along the string. So, this propagating disturbance perpendicular to the string is a wave, and such a wave where the disturbance is perpendicular to the direction in which the wave propagates. So, this is the string, the blue line over here represents the string, and you have disturbed the string perpendicular in the perpendicular direction in the transverse direction. So, the wave propagates along the x axis, the x axis is aligned with the string, and you introduce a disturbance perpendicular to the x axis, perpendicular to the string. So, you pull the string and leave it, for example. So, you will have a disturbance that propagates along the string. This disturbance you represent by y. So, the y is the disturbance of the string, it is the transverse displacement. So, in this situation where you have vibrations of a stretched string, the variable A represents the transverse displacement of the string. So, such a wave is called a transverse wave, and in this case A, the variable A represents y, the displacement of the string in the transverse direction. So, such a wave is a transverse wave, and in this situation A represents y. So, the point I am trying to make here is that we are going to discuss the whole wave phenomena in today's lecture in terms of a variable A. The physical significance of this variable A has to be determined, will be determined by the physical situation that we are analyzing. So, if you are analyzing a particular situation, say sound waves, A will correspond to density fluctuations. If you are analyzing vibrations in a string, waves in on a stretched string, A will correspond to the transverse displacement on the string, and if you are considering some other physical situation, the physical significance of the variable A will change. So, now let us look at the behavior of A as a function of, which we know is a function of x and t. Let us look at how A behaves if I fix the value of x. So, if I fix the position, so there is a wave, there is a disturbance which is a function of both x. So, it changes with x and it also changes with time, changes with position and time. Now, we fix the position. So, we have an observer at a fixed value of x, and this observer observes A, how A varies with time. So, this observer sits at a fixed place, and he or she observes how the variable A could be the density fluctuation, could be the vibration in a string, how this quantity varies with time. So, let us look at this. So, A tilde in the complex notation is okay. Before we look at this, how it varies at a fixed position, let me just give you a few definitions. So, this is the equation of the sinusoidal plane wave. In this equation, the constant A tilde outside is the complex amplitude of the wave. The modulus of this, the modulus of A tilde, which is A, tells us the real amplitude of the wave. So, it gives us the magnitude of the wave, and we define omega t minus kx plus this contribution from the complex amplitude I psi. This combination we define as the phase of the wave. So, the phase of the wave is the quantity that appears in the exponent e to the power I times the phase. So, this wave, so we can also express the wave as A tilde as a function of x t is equal to A e to the power I phi x t. This phi we shall be referring to as the phase of the wave, and this phi is the function omega t minus kx plus psi. Sometimes we shall also refer to this psi as the phase of the wave, and it shall be clear from the context what we are referring to. So, in general we shall be referring to this function phi, which is omega t minus kx plus the phase psi as the phase of the wave. So, the wave has an amplitude A and it has a phase phi x t, and it can be written in this fashion shown over here. With this prelude, let us go back to the question which we were asking. We are looking at the behavior of this oscillation, we are looking at the behavior of this quantity A, which varies with x and t. We are looking at its behavior at a fixed value of x, at a fixed position. So, when we fix the position e to the power at, let us say, x1, so we have fixed the position at x1, A tilde, A is now just a function of time. So, A now becomes a function of time alone, because we have fixed the value of x at x1, and if you fix x at x1, e to the power minus I k x1 becomes a constant, and this constant you can absorb inside the complex amplitude and redefine a new complex amplitude A tilde prime. So, A as a function of t can be written as A tilde prime, where A tilde prime has absorbed this extra phase factor which arises because of this x1, which is constant. So, A tilde as a function of time is A tilde prime, this complex amplitude into e to the power I omega t. Now, recollect that this is just like the simple harmonic oscillator which we have studied. We have a time dependence which is e to the power I omega t. So, you should take only the real part. So, you have a time dependence which is cos omega t. So, what we learned from this is that if you sit at one place and observe the behavior of the wave, you will see that it oscillates, the quantity A now, which is just a function of time, oscillates like a simple harmonic oscillator. So, if you sit at a fixed x and watch the time evolution of A, it will oscillate like a simple harmonic oscillator. So, you could ask the question, after what time period will it repeat? It will repeat. So, let us say that t is the time period. So, if t is the time period, it will repeat when omega t is equal to 2 pi, which essentially tells us that omega is the angular frequency 2 pi by the time period, and it is related to the frequency which is nu by omega divided by 2 pi. So, what we see here here is that if I sit at a fixed value of x, if I have an observer whose position is fixed, then A is going to oscillate like a simple harmonic oscillator. These oscillations are determined by omega, which is the angular frequency of that oscillation. The time period of that oscillation is omega is 2 pi by omega, which you can see from here, and the frequency is omega by 2 pi. So, if you fix the position and look at A as a function of time alone, you have a simple harmonic oscillation of angular frequency omega, where omega is the constant that occurs over here. Let us next look at the behavior of A at a fixed value of time. If you fix the value of time, if you fix the time instant over here in the equation for A, you now have A as a function of the position alone. So, if you look at A as a function of position alone and you have fixed the time instant to t1, so to a particular time t1, you can now absorb this factor e to the power I omega t1 inside the complex amplitude, redefine the complex amplitude with a different phase, where you have absorbed the factor I omega t1. So, the new complex amplitude is A tilde double prime, and you have this factor of e to the power minus I k x. Now, let us ask the question, what does it look like? If you ask the question, what does this look like as a function of x, you should take only the real part. The real part of this is a cosine For convenience, we will assume that the phase of A double prime is 0. So, you have cos kx. So, as a function of x, A looks like cos kx, which is what I have shown here. Now, let us ask the question, after what distance does this function repeat? After what distance does A repeat? We know that cosine repeats whenever the argument assumes a value goes from 0 to 2 pi, and the period, the distance after which A as a function of x repeats is called the wavelength. So, here I have shown you A as a function of x, and you can see that the value which is there over here is there again over here, and the whole function repeats after this distance, which is called the wavelength. So, at a fixed time, the x dependence is sinusoidal, it is either cosine or sine, and it repeats whenever the argument of cosine is 2 pi. So, this gives us the condition that k and the distance after which it repeats is called lambda is equal to 2 pi. So, by definition, the value of A repeats after a distance lambda. So, the condition is that k into lambda should be equal to 2 pi, because cosine and sine both repeat after a phase of 2 pi, phase difference of 2 pi. So, which tells us that k, which the number k, the constant k which appears in the equation for the sinusoidal plane wave, is related to the wavelength by k is equal to 2 pi by lambda, and k is called the wave number. Lambda is the wavelength and k is called the wave number. So, let me now summarize what we have just learned. A as a function of x and t in the complex notation, if it can be written as some constant, complex constant into e to the power I omega t minus kx. This is a sinusoidal plane wave. It has an amplitude. The amplitude is the constant which occurs outside this whole thing. In this case, it is the complex amplitude. We also have two constants which appear in this expression, omega and k. Omega is the angular frequency. So, if I fix x, I will observe oscillations just like a simple harmonic oscillator, and these oscillations will have an angular frequency omega. If I fix time, I will see A varying as cosine with x, and the period of this cosine is called the wavelength, and k is related to the wavelength, and k is called the wave number, and it is k related to the wavelength through the expression given over here. Lambda refers to the wavelength, and the wave number k is related to the wavelength through the expression given over here. So, we have now individually studied the dependence of the behavior of the wave if I fix the time, and then we studied if I fix first we studied if I fix the position, how does it depend with time. We then studied what happens if we fix the time and look at the variation with position. Corresponding to this, we got the angular frequency, corresponding to this we got the wave number. Now, in summary then we see that the wave number tells us how the phase of the wave varies with position, right, and it is the derivative, the rate of change of phase with position. So, the wave number k tells us the rate of change of the phase with position. It is minus del phi del x, right, and you can just check for yourself that if you differentiate the expression for the phase, if you differentiate the expression for the phase with respect to x and put a minus sign, you get the wave number. So, the wave number tells us the rate of change of phase with position, and the angular frequency with the negative sign. The angular frequency tells us the rate of change of phase with time. So, as time evolves, how does the phase change? That is the angular frequency. if you move from one place to another, how does the phase change? That is minus the wave number. Okay. So, we have learnt about a plane sinusoidal wave. We have seen how it depends if I fix time. We have seen how it depends if I fix the spatial position. Let us now study the combined space and time dependence of this wave. So, the thing which comes up when you study the combined space and time dependence of the wave is the phase velocity. So, we are going to study the combined phase the space x and t dependence of this equation. Now, the value of A is essentially determined by the phase phi, which is a function of x and t, and the phase phi is omega t minus kx. Let us ask the question at t equal to 0, where is the phase, where does the phase have a value 0? So, you can see it is quite straightforward that at t equal to 0, the phase phi assumes a value of 0 when x is equal to 0. This is what I have shown over here. Now, the next question is, as time increases, as time evolves, so time starts, we start our discussion at t equal to 0, we start studying the whole thing at t equal to 0, and then we want to see what happens as time increases. And the question that we are interested in is, how does the point where the phase is 0 move as time increases? So, we will follow the point, we will follow the position x where the phase is 0, and we will follow this point as time increases from t equal to 0. We know that this point is at x equal to 0 when t is equal to 0. We want to follow the evolution with increasing time. So, this graph allows us to follow the motion of the point where the phase is 0. The black curve over here, AX0, shows you the behavior of x at the time t equal to 0. It is a sinusoidal curve, it is actually it is cosine kx, at t equal to 0 it is cos kx, and the phase phi, which is omega t minus kx, at t equal to 0, the phase phi has a value at x equal to 0. So, this is the point, this is the value of x where the phase is 0, and cos omega t, cos phase, has a value 1 over here. So, this is the point at t equal to 0, this is the point where the phase is 0. Now, as if time increases, so time has increased from t to t plus delta t. Question is, how much should x change if the phase has to still be 0? So, initially the phase is 0 where both these variables are 0. Now, time increases from t to t plus delta t. So, we want the phase to be 0. So, delta x, the change in x, has to be such so that it exactly balances this. So, the change in x has to be omega by k into delta t. So, if you take this change in x and put it in here, then you will find that the phase is again 0. So, after a time delta t, the phase is 0 at the point delta x, which is omega by k into delta t. So, after a time delta t, the point where the phase is 0 has moved a distance which is delta x, which is equal to omega by k into delta t. So, after a time delta t, the point where the phase is 0 has moved from here to here. Now, you could have done the same thing for any other value of phase. There is nothing special about the phase 0. You could have taken a value of the phase pi by 2, which is this point here initially. This is the point where the phase is pi by 2. So, initially the phase is pi by 2 at this point, and you could ask the question, after a time delta t, where does the phase become pi by 2? So, after a time delta t, the phase is pi by 2 over here. So, the point where the phase is pi by 2 has moved the distance from here to here. And it is quite clear that for any value of the phase, if you follow the position where the fixed value of the phase has shifted after a time delta t, you will find that it has moved a distance delta x, which is omega by k delta t. So, what we learn from this is that the position where the phase, if you follow the position where the phase has a fixed value, for example, if you follow the position where the phase is 0, you will find that it moves forward as time increases, and it moves forward at the speed omega by k. So, this speed is what is called the phase velocity. So, the point where the phase is 0 moves forward at a speed which is called the phase velocity, and it is not only the point where the phase is equal to 0, any fixed value of the phase moves forward at the speed omega by k. So, that is quite obvious, right. If you are looking at the phase x t is omega t minus kx, and we are following the point where the phase is 0, and you can, it is obvious from here that this point will move along the trajectory x is equal to omega by k into t, and so it will move in a straight line with a fixed velocity. It will move in a move at a fixed velocity. This velocity omega by k is what is called the phase velocity. So, the phase velocity is the speed at which the phase of the sinusoidal plane wave propagates. Remember that the phase had been defined in this fashion: phi x t is omega t minus kx, and I could have a constant psi. So, if I look at the speed at which a fixed value of phi propagates, this speed is called the phase velocity. So, you should note that the phase velocity can only be defined for a sinusoidal wave, right. It is only for a sinusoidal wave that I have a fixed angular frequency omega and a fixed wave number k. So, you can define a phase, and you can then ask the question, at what speed does the phase move, and this is the phase velocity omega by k. So, having told you the phase velocity, let me now again show you a picture of how the wave evolves. So, this is the wave. The black curve shows you the wave at t equal to 0. After a time t 1, so at t equal to 1, the point where the phase is 0 has shifted forward. It has shifted forward by 1 into the phase velocity. So, it has moved here, and the same with every other point, it has moved forward by the same amount, because the phase has moved the same amount. So, the value, the point where the phase was pi by 2 has shifted by the same amount, and all intermediate points have shifted by the same amount. So, the whole curve moves forward, and then after some time t, at some time t equal to 2, it moves forward again further, and t equal to 3, it moves even further. So, this is how the whole thing evolves in time. In time, the whole wave, the form of the wave does not change, it just moves forward in time. So, this shows you the wave propagation as a function of time. So, you can see that the whole sine wave or cosine wave just moves forward in x as time propagates. So, let me show it to you again. As time propagates, the whole pattern just moves forward. So, we have studied waves, disturbances, which are a function of one variable x and time. So, the thing that we have been studying until now is a as a function of x and t. Now, such a discussion may be adequate, is adequate if you are dealing with disturbances, for example, in a string. On a string, if I put a disturbance, it will propagate along the direction of the string. One variable x is sufficient to parameterize, to label the different points on the string, because the string is effectively one dimensional. So, such a description is adequate for that purpose. But if I have, for example, sound waves, sound wave in this room can propagate, in this room is 3 dimensional. So, the sound wave in this room is actually a function of 3 coordinates. So, we need 3 coordinates to describe different points on the room, and the sound wave in this room will be a function of 3 independent coordinates. So, in general we shall be dealing with, we have to deal with waves in 3 dimensions. The space that we live in is 3 dimensional. So, for like this room. So, in 3 dimensions you require 3 coordinates. So, here we have 3 different coordinates x, y and z, and any arbitrary point in the room could be the, with reference to an origin I could refer to any arbitrary point using the vector r. So, with in this room or in any 3 dimensional space I could choose 3 axes like this, x, y and z, and I could have a vector to any point. This vector r corresponding to different points, the vector r will have different coordinates x, y and z. So, in 3 dimensional space any arbitrary corresponding to any arbitrary point I have a vector which goes from the origin of my coordinate system to that point, and this vector is described, is completely specified in terms of 3 coordinates x, y and z. I, j, k here are unit vectors along the x axis, y axis and z axis. So, I have I, j and k. These are unit vectors along the x, y and z axis. Now, so we are working in 3 dimensions. Let us first interpret the wave which we have been studying until now in a 3 dimensional context. So, the wave which we have been studying until now is A, which is a function of r. By r we mean all 3 x, y and z. So, A is a function of r, it could vary from point to point in the room, and we will be analyzing the expression which we had been studying until now. So, what we had been studying until now, there was an amplitude here, and we have e to the power, there should be a I here. So, there should be a I over here. So, there is a I which is missing here, you can put it in here. So, we have e to the power I omega t minus kx. So, this is the wave that we had been studying. So, it only depends on x, it does not depend on y and z, and we are going to interpret this in a 3 dimensional context. Now, let us ask the question, what does the phase, let us look at the phase of this wave. The point to note is that the phase of this wave depends only on x, it does not depend on y and z. So, if you have a displacement in 3 dimension which is along the y axis or along the z axis or a combination of these, the phase of the wave does not change. The phase only changes if I move along the x direction. So, this tells us that there are surfaces in 3 dimension, there are surfaces on which the phase is a constant. These surfaces in 3 dimensions on which the phase is constant are parallel to the y and z axis. So, if I move along either the y z axis, anywhere along in the y z plane, the phase does not change. So, there are surfaces, these surfaces are parallel to the y z axis, y z plane, and the phase is a constant on these surfaces. The phase only changes if I move along the x axis, it does not change if I move in the y z plane. So, there are these constant phase surfaces. These constant phase surfaces are what are called wave fronts. So, there will be a surface which is x equal to 0 where the phase is 0. Then I will have another surface where the phase would have increased, and here I show you these surfaces on which the phase has a constant value. These surfaces are perpendicular to the x axis because the phase changes along the x axis. If I move perpendicular to the x axis, the phase does not change. So, the constant phase surfaces are perpendicular to the x axis and they are parallel to the y z plane. So, these are the constant phase surfaces, these are what are called wave fronts. So, the point to note is that in this situation where I have a wave which looks like this: a e to the power I omega t minus kx. The wave fronts are planes. There are planes on which the phase is a constant, which is why this is called a plane wave. Right? I could have other kinds of wave fronts also which are not planes, and then they would not be plane waves, but in this situation, which is the simplest situation, the wave fronts, the constant phase surfaces are planes. These planes are shown over here. These planes are perpendicular to the direction of propagation of the wave. In this case, they are perpendicular to the x axis. So, we have these wave fronts on which the surface, the wave fronts on which the phase has constant values. Now, what happens to these constant phase values as time evolves? So, we have all just seen just a short time ago that at a later time the value of x where the phase is 0 moves forward, it moves forward at the phase velocity. So, this is what happens here also. So, at a later time the value of x where the phase is 0 has moved forward. So, this whole plane where the phase is 0 has moved forward, and so with time what happens is that these wave fronts, the constant phase surfaces, move forward along the x axis. So, in this case the constant phase surfaces move along the x axis. So, as time evolves the constant phase surfaces move along the x axis. Let me, so this picture shows you how the wave fronts evolve in time. As time evolves, the constant phase surfaces move along the x axis. Let us now discuss a wave in an arbitrary direction. Until now we have been discussing a wave in 3 dimensions, but the wave was propagating only along the x axis. The next question that we shall discuss is, how do you represent a wave propagating in an arbitrary direction? To understand this, let me first tell you the answer, and then I shall explain to you why it is so. So, you can represent a wave in any arbitrary direction as a, it is now a function of r and t. R is a vector in 3 dimensions. So, a is a function of r and t, and a wave in any arbitrary direction can be represented as the complex amplitude into e to the power I omega t minus k dot r. So, we earlier had k into x, we now have replaced that by k dot r. Now, the first thing is that this vector k is called the wave vector. We have replaced the wave number by a wave vector. So, when you are dealing with waves propagating in 3 dimensions, you have to replace the wave number by a wave vector. If the wave is propagating along the x axis, you have to choose the wave vector to be the wave number k into the unit vector along the x axis. So, if you put this into this expression, you will recover k into x, where k is the modulus of this wave vector, k is the amplitude of this vector, and a is the unit vector along the x axis. So, when you put this in here, you get k into x. So, if you put this over here, you get kx. You recover the wave propagating along the x axis. Now, if you want the wave to propagate not along the x axis, but in some arbitrary direction with unit vector n. So, n over here is the unit vector in which you want the wave to propagate, not the x axis, but some other direction. Then the wave vector should be the wave number k into the unit vector n. So, if you use this wave vector in this expression, this wave will now propagate along the direction of the unit vector n. It will have a wavelength which is 2 pi by k. This wave number continues to be related to the wavelength by with a factor by a factor through a factor of 2 pi, and then you take the inverse of the wavelength, you will get the wave number. So, this is how we can represent waves in arbitrary directions. So, let me now show you what this looks like. I have a wave in 3 dimensions. The wave is propagating in this direction n. So, this n over here is the unit vector in the along the direction in which the wave is propagating. So, I have a wave which is propagating along the direction of the unit vector n shown in the slide. Okay. Now, let us just look at the equation representing this wave. So, the equation representing the wave is shown over here. Let us ask the question, in which direction does the phase change? So, it is quite clear that the phase changes only along the unit vector n. So, if you move in a direction perpendicular to the unit vector n, the phase does not change. So, from this you conclude that the wave fronts are orthogonal. So, you have a wave direction n along which the wave is propagating. If you move in a direction perpendicular to that, the phase does not change. So, the directions perpendicular to the unit vector n are the wave front. So, this is what is shown over here. These planes are perpendicular to the direction n, and these are the wave fronts. So, if you move from here to here, the phase does not change, and these are the wave fronts. So, as time evolves, these wave fronts will propagate forward. The whole wave front, these whole set of wave fronts will propagate forward. So, this is what the wave fronts look like if I have waves propagating in an arbitrary direction. Now, let us ask another question. How much does the phase change? How much does the phase change if at a fixed time I look at 2 different points? So, the question we are asking is, what is the phase difference between this point and this point? So, the question we are asking, let me repeat it again, is at a given time t, what is the phase difference between this point and this point? Now, remember that if I move in the direction perpendicular to the n, there is no change in phase. So, it is only the component of the displacement delta r along the direction of the wave, along propagation of the wave along n, that gives rise to a change in phase. So, we go back to the expression for the phase as a function of the position and time is omega t minus k dot r. So, we are interested in the phase difference between 2 points, one point being r, the vector r, the other point at the position r plus delta r. So, the difference in phase between these 2 points, delta phi, is minus k dot delta r. So, the phase difference arises only due to the component of the displacement in the direction of propagation of the wave, and it is minus k, the wave vector, dot delta r. This is something that is going to play an important role later on when we discuss interference and diffraction, various such phenomena where we superpose waves. So, it is quite an important relation. So, this brings us to an to the end of our discussion of plane sinusoidal waves. Plane sinusoidal waves are essentially, if I sit at a fixed place, I will see an sinusoidal simple harmonic oscillation. If I look at the variation with position at a fixed time, I will see again a sine wave, sine function which varies with position. So, a position dependence which is sine or cosine, and with time the whole pattern moves forward along the direction of propagation. So, having completed our discussion of sinusoidal plane waves, let us take up a simple problem where we can apply some of the things which we have learned. So, in this problem that we are going to discuss, we have a wave, and the wave is described by a wave vector. The wave vector is 4I plus 5j meter inverse. The wave also has an angular frequency which is 100 megahertz. Remember that it should we could have written radians per megahertz, radians per radians per 10 to the power 6 second 10 to the power 6 per second. So there could have been a radians here, but we are not mentioning it explicitly. So omega has a value 100 megahertz. Okay. So the first question that we are going to ask is, what is the wavelength of this wave? How will you determine the wavelength of this wave? To determine the wavelength of this wave, you have to first calculate the wave number. So the wave number is the modulus of this vector. So the modulus of this vector, this vector has x component and y component. So the modulus of this vector is the square root of 4 square plus 5 square, 4 being the component along the x axis, 5 being the component along the y axis. So the modulus of this vector is the square root of 4 square plus 5 square. This is 16 plus 25, 16 plus 25 is 41. So this is the square root of 41, and the units are meter inverse, and the wavelength lambda is 2 pi by the wave number k, it is 2 pi by the square root of 41 meters. The next part is to calculate the frequency. We know that the frequency of the wave is related to the angular frequency through this. So you have to just plug in the value 100, this will be 100 megahertz divided by 2 pi. So we have worked out the first two parts of the problem. Let us now calculate the phase velocity of the wave. The phase velocity is omega by k, and omega has a value 100 by 2 pi, and we can go directly to hertz. So this is the value hertz, and k has a value which is root 41 meter inverse. So the phase velocity has a value 100 rather 10 to the power 8 divided by 2 pi root 41 meters per second. So this is the phase velocity of the wave.